In this video lecture, I'll be talking about the static equilibrium, uh, and this is a very short lecture, and you're just gonna need a very, simple problem for the upcoming exam. So we're gonna talk about the equilibrium conditions, the static equilibrium conditions, and we will apply these conditions to a variety of practical engineering static equilibrium problems. So just to get started, if you have a point mass, small point mass, and if it is acted by two equal and opposite forces, then the particle will be in equilibrium, right? The particle won't move, and it is in static equilibrium. So what happens if you apply the force, same equal and opposite force, like this on a block instead of a point mass? Will it still be in equilibrium? And the answer is yes, because of this condition, because the net force is zero still, right? Equal and opposite. Net force is zero, and net torque is also zero, because the way you apply force, exert force here, will not produce any rotation. So net torque is also zero. So when a particle is made by this condition, the net force is zero and net torque is zero, this is called static equilibrium. So now let's see a slightly different picture. So the same block, say, is being acted by two equal and opposite forces, but slightly different positions, something like that. So will it still be in equilibrium? And the answer is no, because the way the forces are acting here will produce the rotation now. So in this example, it is this couple of forces, are producing a clockwise rotation. So although the net force is zero, net torque is not zero, because it produces rotation. So then you have to say this rigid object body is not in static equilibrium. Okay, so these are the conditions. Here's the important conditions. So if an object is in static condition, static equilibrium condition, the net force has to be zero. So that means the all the components, the x component, y component, and z components has to be zero, and the net torque also follow the same rules. Net torque has to be zero, and then you can say that the given object is in static equilibrium, right? And and using the Newton's second law, you can say that the net force is zero, then it's the total linear momentum, remains constant, right? Net force is zero, the net uh, the linear momentum also doesn't change. And also, if the net torque is zero, the angular momentum also doesn't change. But since in this topic we are talking about the static equilibrium, not just equilibrium, because an object could be moving or rotating and still the net torque could be zero. But here, since we are talking about the static equilibrium, so we want to make sure that is the object is not moving and the object is not rotating. That's we call static equilibrium. In addition to these rules. So now next, I'm gonna show you some, and in this examples, all these pictures are examples of static equilibrium. All these objects are perfectly under static equilibrium conditions. These objects are not moving, so no translational motion and no rotational motion. So next, I'm going to show you some examples of static equilibrium problem, and this page describes the main recipe of using static equilibrium problem. So first, you have to draw a clear free body diagram showing your distance, your position vector, and force, and the angle between them. And then your next job is to choose your convenient origin. So always choose a origin or pivot point where unknown forces are acting, because if you do that, then you can just ignore the force, those unknown forces. You don't need to know those forces, because torque about that pivot point is zero due to these unknown forces. And then after that, using the right hand rule, uh, apply the torque rule and apply the static equilibrium conditions, this, and then you'll have bunch of equations, number of unknowns, number of equations, and solve them to find the given conditions. So now next I will be showing you the actual problems. So let me show you some example problems on static equilibrium. So here's the problem. This lady is standing on a platform bar, and the platform itself actually stands on two mass scales, and it's asking what's the scale readings. These two mass scale, what's the scale reading in newtons. So the lady is 60 kilogram and the mass of the beam is 80 kilogram. So the rule is, when you solve static equilibrium problem, the first rule is draw a clear free body diagram, force diagrams. So here, first of all, the scale reading, mass scale reading, is the normal force that it experiences because the platform is standing here. So there will be, let's say this is normal force, N1, and this is normal force N2, which are unknown normal force. Mass of the lady is right here. I'm gonna say weight of the lady, and mass of the beam, which acts right at the center of mass, right, which is at this weight of the beam, right. I guess that's all the free body diagram on the beam. So these are the forces acting on the beam. So the next step before we apply the static equilibrium condition, next step, remember, if you remember the recipe, is to choose the appropriate origin. So always choose a origin where unknown force is acting. So we don't know N1 and N2, right? So you can choose one of the origin. It doesn't really matter where you choose the origin. Let's choose this as my origin. So choose this as origin, right? And then after that you just apply the static equilibrium conditions. Remember, this everything is in static equilibrium condition. So the net torque has to be 0 and the net force has to be 0, right? So here we're going to apply, first we're going to apply the net force, net torque is 0 condition, right? So the net torque, because torque is always about the pivot point, so here we choose the origin. So the net torque about the origin we have just chosen is tau net, sigma tau is torque due to N1 plus torque due to the weight of the beam, right, plus torque is a vector quantity, torque due to the lady, and plus torque due to N2. And remember, our general formula for torque, magnitude of torque, is Rf sine theta, and to find the direction you use the right hand rule. Okay, so and this all has to be 0. We know that because this is in static condition, the net torque has to be 0. So net torque, what is this? This would be 0, right? This normal force N1 would not produce any torque because we have chosen this as our origin, and the radius position vector R is 0. So this is 0 torque. So torque due to the beam, and remember this beam, the weight of the beam acts here, so this is trying to produce clockwise torque, right? So it's a negative torque. Remember, clockwise is negative torque. So R is L over 2. Rf sin theta is our main formula for torque. Force is weight of the beam, which is mass of the beam, gravity, and it makes 90-degree angle, all this. So lady is also producing clockwise torque, so negative torque, and the lady is at 1.5 meter distance is given. F, which is the weight of the lady, mass of the lady times gravity, and sine of 90 degree. Finally, the torque produced by the second normal force, and it produces the counterclockwise torque, right, about this origin. So it's trying to produce counterclockwise torque, and that's why this is plus, which is at the distance of L, whole distance. Force is N2, right, and sine, all these angles are 90 degree, so all equal to 0, right, so all equal to 0. And you put L, the value of L, the length of the beam is 2 meters, put L as 2 meters and solve for N2. If you solve for N2, you're going to get 833 newtons, right. This is the scale reading here. This is the mass scale reading. This scale would read 833 newtons. Now we still need to find out N1, which is the first mass scale reading. And how do you find that? Then we're going to use the second static equilibrium condition, which is the net force. So here net force in y direction 0, right. This is also one of the static. So then let's apply this. So you have N1, right, in y direction, minus mass of the beam, gravity, minus mass of the lady, gravity, and plus N2. All this makes the sum of the forces in y direction 0. And then if you put all the numbers, because you know everything, N2 is this, right, everything, then you can solve for N1. And N1 is, if you solve that, you're gonna get 5. So these are the answers. So the first mass scale reads 539 newtons. Second mass scale would read 833 newtons. So here's an example animation, applet animation of static equilibrium problem. This bar, metal bar, is supported by a cable. So one end of the bar is supported by a cable, the other end of the cable is just hinged on the wall, and the other end of the bar is also hinged at the wall. So an extra mass is just placed at some position on the bar, which you can change. So you can change the position of the extra mass and see how tension will change, with the position of this mass. And also you can change the angle that the cable makes with the bar, and you can check how tension, the force of tension on the string, on this cable changes. As you can see, first put this this extra mass at fixed position, and then let's check actually if how the tension force changes. So as you can see, right, as you if you make less steeper like this, the tension will increase with decrease in angle, as you can see, and the tension will is almost inversely proportional to the angle you make. And same thing actually. So let's change the position of this extra mass. So you can clearly see, right, the tension decreases if you move the extra mass to the left, and tension increases, right, same way. And you can play with the different parameters here. And also one more thing I will show you. So before you solve the static equilibrium problem, remember you will have to show the clear free body diagram. So this will be the free body diagram at this position. This is the tension force, this is the mass of the beam, which is at the center of mass. This is the mass of the extra mass box, and this is the position of the hinge. So and the hinge force has two components, right? We don't know the actual resultant position, but we do know that there are two components of hinge forces, the horizontal hinge force component, the vertical hinge force position, which we can solve, using the static equilibrium conditions. And you can also see the equations, the actual equations to solve this problem. It's a very helpful applet. So next, this is the next problem as explained in the applet. So here this beam, steel beam, beam is supported by a cable. The cable is hinged here, right, and the beam is also hinged here, and it says the maximum tension this cable can withstand is 15,000 newtons. And it's asking, should the worker be worried? The worker is actually, this construction worker is sitting, 2 meters from the right end. So here from his center of mass to the right end, it says based on the question, he's standing, at he's sitting 2 meters from the right end. So so let's choose this as our origin, right? Usually we choose the origin where unknown forces acting. Here you have hinge forces which are unknown. So it's just, you just need to now find the tension in this cable and compare with this maximum tension, right? That's all you need to do. And if the tension in the cable is less than this, he's safe. If the tension in the cable is, however, more than this maximum limit, then yeah, this worker shouldn't sit down here. That's what we're. So let's draw the free body diagram. So you have weight of the beam, weight of the worker, and this is the tension, right? And you have this unknown hinge forces. This is the horizontal component hinge force, this is the vertical component, right? We don't know the resultant, but we do know horizontal and vertical hinge forces, which you don't need to worry about. It's not acting the hinge forces. Since we choose the origin here, you don't need these hinge forces. So we're going to apply again the static equilibrium condition. We know that the net torque above this origin chosen has to be 0. So same thing here. So you have 3 torques. The torque produced by this hinge forces will be 0 because this is the origin. So you don't need to worry about these unknown forces. So first is the torque produced by the beam vectors plus the torque produced by the worker plus the torque produced by the cable has to be 0 by static equilibrium condition. So what is the torque produced by the beam? And also it's a vector quantity, it has some direction. If it is clockwise, it's negative. If it is counterclockwise, it's positive, right? So the torque produced by beam is about this origin is trying to produce clockwise rotation. So it's a clockwise torque, so negative. So RF sin theta, right? Torque is magnitude is always RF. So R is this position vector, which is half of length of the beam, right? And mass of the beam, gravity, sine 90 degree. The worker is also trying to produce the clockwise torque, so that's why negative torque. But this distance is now you're gonna need this distance. So this is 2 meters from the right end. So from the origin it will be 4 meters because total is 6 meters. So 4 meters is your R. F is mass of the worker, gravity, sine of 90 degree. Now finally the torque produced by the cable. So about this origin you have to use your common sense. It's trying to produce this torque, right, which is counterclockwise. So from right hand rule is positive torque, right? So positive, so R is the whole length of the beam, force is the tension, sine of, it says it makes 30-degree angle. So it has to be equal to 0. So again here L is the length of the beam. It says length of the beam is 6 meter, right? And put 6 meter as L here, everything, and you solve for the tension. So tension in the cable is, if you solve for 15,000 to 55 newtons. And let's compare with the maximum tension from the manufacturer. So manufacturer says the cable can withstand a maximum of only 15,000 newtons. Since tension in the cable, right, is greater than tension in the maximum tension limit, the worker, right, should be worried. Actually, worker should not sit on that position, right, because the cable might break. Okay, so that's how you solve this problem. So another similar problem, right? Similar problem. This is a similar static equilibrium application in engineering design. So here's the some sign. You know, um, and this again beam is hinged at one end. The other end, is somewhere at some distance x is supported by a cable. The other end of the cable is again supported by the wall. So it's asking, first question is, what's the tension in the cable, right? Just in terms of the symbols, all in terms of the symbols, right? And the unknown hinge forces, next question. Okay, so first, so the best place to choose the origin is this, right? Why? Because you have unknown hinge forces acting here. You don't know that. So we call it FFH and FF vertical, which we will find in second part. And you have tension in the cable, and you have at the center of mass is weight of the beam, and here you have, right, weight of the sign. So these are the forces acting. And then to find the tension, you have to apply the first condition, one of the condition of static equilibrium, the net torque, about that, the origin we have just chosen, right, has to be zero. So here the torque produced by this unknown hinge forces will be zero, because we have chosen this as your origin. R is zero, right? So there will be one, two, three torques, right? Three torques here. So torque produced by the weight of the beam, which is again clockwise, is negative torque. So L over 2 mass of the beam, gravity, it makes 90-degree angle. Again, torque produced by the sign is also negative because it's clockwise. It's at L, right? L distance, full distance L, and weight of the sign is mass of the sign, gravity, sine of 90-degree. And one more, finally, similarly, right? So torque produced by the cable, tension in the cable is, however, counterclockwise. If you use the, right, if you use this rule, is out of z positive z axis plus, but this cable is hinged at x distance, not L, at x. So the R is x, force is T, and sine of it makes angle 30 degree, which, so we're going to solve all these in terms of symbols. So now sine 90 is 1. So now if you solve that, the tension in terms of all symbol will be Lg. So I have the mass of the sign plus mass of the beam divided by 2 whole divided by x sine theta. And if the numbers are given, the last part numbers are given, you can just put the numbers and then solve it. So second part now is it's asking what are those unknown hinge forces, and that's also easy. Then you have to use the other condition of static equilibrium. We know that sum of the force in x direction is to be 0, right? So let's find out all the forces, x forces. So you have one horizontal hinge force. This is the hinge force, horizontal component hinge force, right? And these are vertical, so you don't need to worry. But the tension, the cable has two components, and this is the negative component, right? The x component of the tension is negative t cos theta. That's it. These are only the two forces acting on the beam horizontally. So the sum of the horizontal force, the horizontal hinge force, horizontal hinge force is just t cos theta. So similarly, you have to apply the sum of the force in y direction 0 to find the y component of the hinge force. Is now the y component of vertical force of the hinge, right? And minus weight of the beam, mass of gravity, mass of the beam, gravity, minus mass of the sign, gravity. And one more thing, don't forget the components of the tension. So t sine theta, right? Because this is in second quadrant. This y component is positive t sine theta is equal to 0. And then you can figure out the vertical component of the hinge force, and that's going to be, and solve for. So I have the answer for that. So mass of the beam plus mass of the sine times gravity minus t sine theta. Should get that, right? So this is your answer. It's the horizontal hinge force, vertical hinge force, and then you can find the resultant. So one more problem. So again, this beam, is hinged on the wall. The other end is supported by the cable, and cable is again attached, rigidly here, and these are the angles, given 30-degree angles it says. But this bar in this case is not horizontal, right? It's making some angle, and it's acting. What's the tension in the wire? Tension in this cable, right? So free body diagram will be something like that. The weight of the beam acts right at the center of mass. This is the weight of the beam, right? And there's no other extra masses, so you have cable tension, and you have some unknown hinge forces which you don't need right now because it's just acting the tension. So this is the horizontal component of the hinge force. This is the vertical component hinge force, and let's choose this as our origin for simplicity, right? And we're going to calculate the torque about this hinge force. So since we have chosen this as our origin, you don't need to know these unknown hinge forces, right? And that's it. So first, be a little careful here. When you calculate the torque due to beam, you're going to need this angle, right? This angle, because this is your R, this is your F. So what would be this angle? So that you're going to need, and to do that, so this is 30 degree, right? Given 30 degree. So what would be this angle? So this angle will be, sum of these three has to be 180 degrees, so it has to be 120. But this flat side, this horizontal 180 minus 120, this has to be 60 degree. If this is 60, this is also 60. You're going to need that to calculate the torque produced by the beam. So then we're just again, since it's just acting the tension in the cable, we can just apply one condition. The net torque about this origin, right, has to be 0. And there's only two torque due to the beam, right, plus torque due to the cable, because the torque due to these unknown hinge forces you don't need, because that will be 0 anyway, right, because we have chosen this as our origin. So torque due to beam, again, this is about this origin. See here, it's trying to produce clockwise rotation, clockwise torque, so that's negative torque. So distance is half of L2, half of the length of the beam. Force is mass of the beam. The weight is directly given, so you can just do W of beam. And sine of here, not 90 degree, because the beam is not horizontal, right? So it's 60 degree, because in torque formula, right, RF sine theta, this theta is the angle between R and F. So here is 60 degree, right? And torque due to cable is positive because it's counterclockwise torque, so positive. And this distance, whole distance is L T sine of not 60 degrees, 30 degree, right? Because this cable is making 30 degree. That's it. And so you don't even need L will cancel out here, right, anyway. And you can solve for tension here, right? Weight of the beam is given, and it's going to be 188 newtons.